that we can actually achieve it with actual calculation. Like the calculations may be too much for us. Here, I can show you a fourth order one we can do. X squared minus 81. Excuse me, x to the fourth minus 81. So this one's kind of a trick, but when we look at this is x squared squared, right? Minus 9 squared. So it's the difference of squares. So I can do the difference of squares thing, you know? I can rewrite this as x squared plus 9 times x squared minus 9. Now the x squared plus 9, we recognize from our discussion today, I hope, that's a what? Can that be factored? X squared plus 9. Can this be factored? No, this is irreducible, right? We have a square plus something. It's irreducible. So this is the end of the road. This piece we're done with. Irreducible, done. On the other hand, over here, we have what? Difference of squares again, right? 9 is 3 squared. So that can be written as x squared plus 9 times x plus 3 times x minus 3. And there you go. We have completely factored this fourth order polynomial. So there are special examples of fourth orders which you can do, but they're really special. They're really not very common, right? The same is true of third order problems. If I just give you an arbitrary third order problem and ask you to factor it, that's an unfriendly question. Because generally speaking, it's pretty hard to factor a cubic, right? Unless there's some kind of special pattern, right? Like you can factor out an x. See this one? If we had x cubed plus 6x squared plus 5x, we could factor the x out, right? Factor the x out, we'd have what? X times x squared plus 6x plus 5. Now, this one, I don't think we need to complete the square for this one. I think we can guess and check this one. The numbers are pretty nice. Again, the philosophy I'm trying to get you guys to adopt is if you get stumped on the guess and check, fall back on completing the square. It's kind of like a weapon of last resort, you know. So to get 5, I do what? 1 times 5? And 6 is what? 1 plus 5, right? So I do plus 1 and plus 5. So see, that kind of cubic, it's pretty easy to factor, right? Let me show you one that's not. X cubed plus 6x squared plus 12x plus 8. Question mark. All right. So to solve this problem, I'm going to introduce you to a new tool. This is called Pascal's triangle. So Pascal's triangle works like this. You put a 1 here, put a 1 here, you put a 1 here, you put a 1 here, you put a 1 here. Now, add these two numbers, we get 2. Right? Put a 1 on the outside. I add the numbers above. I get 3. I get 3. All right? I put a 1 here. I put a 1 here. You guys tell me what goes in the next row here. 4, 6, 4, right? So let me tell you the meaning of each row as it relates to algebra. The first one's kind of boring. The first one says that a plus b to the 0 power, well, it's equal to 1. The second one, which doesn't really have much application, a plus b to the 1 power is a plus b. See, the point is the coefficients of a and b are 1 and 1. A plus b squared, well, that's a squared plus 2ab plus b squared. See, the coefficients are 1, 2, and 1. The pattern is that a starts at its highest power and decreases to 1. B starts at 1 and it increases to its highest power. So as a is increasing, b is decreasing, and they just kind of pass each other. That's the pattern. So a plus b cubed, what's that? Well, that's a cubed plus 3a squared b plus 3ab squared plus b cubed. And not that we'll probably need it this semester, but this last row here shows me that a plus b to the 4th power is a to the 4th plus 4 a cubed b plus 6 a squared b squared plus 4 ab cubed plus b to the 4th. It's not hard to see that Pascal's triangle gives us a way to expand a plus b to a large power far, far faster than it would be if we just did it by hand and used this distributive property over and over again, right? Because there'd be a lot of terms. You think about it. A plus b to the 4th, that's a binomial times a binomial times a binomial times a binomial. In principle, there are 16 terms, right? But those 16 terms do what? They collapse down like this. Notice that the sum of these numbers is 16. 1 plus 4 is 5. 5 plus 6 is 11. 11 plus 4 is 15. 15 plus 1 is 16. That's not an accident. Those 16 terms collapsing down. All right, anyway. There's your quick introduction to Pascal's triangle. How does that relate to this cubic I wrote? I'm telling you, we can look at this as a cubed plus 3a squared b plus 3ab squared plus b cubed, right? That's what I'm telling you. Not every cubic is like this, but this is a special one. So if you look at this, we're going to put b equals to 2, right? Of course, a equals to what? X, right? Does that check? What is a squared? So a squared is x squared. What's b? B is 2, right? So we have 3 times b, which is 6. That's where the 6 comes from. How about this? 3a, well, x is the a. 3b squared is 3 times 2 squared. That's 12. 3 times 4 is 12. So that matches that pattern. And then 2 cubed is 8. So in fact, this cubic is exactly x plus 2 cubed. Now, if I give this kind of problem on the test, it is worded in such a way like, this cubic is a perfect cube. You could use Pascal's triangle to factor this, or something like that. I mean, I would give you a lot of guidance on this kind of problem. And probably it's not on the test, honestly, because it's probably not in your homework. So anyway, that's it for today, guys. If you came in late,